Record. All right. So again, the reason we're doing this is so that we can get this information out so Team Red or whatever can come in and do the laboratory. So basically, we know a lot of this already. Exothermic reactions, they give heat off to their environment, or what I'm going to call the surroundings. Basically, there's two things. There's a universe, and there's what you're looking at. And what you're looking at is called the system, and everything else in the universe is a surrounding, right? What's in our universe? What's probably close enough to our in our universe that affects us hugely every day? The sun, right? The sun is not very close to us, but it affects us hugely every day, right? Does the Earth gain energy from the sun? Yes, quite a bit of energy, right? Quite a bit of energy. Does Pluto gain energy from the sun? Yes, it does, right? But it's probably a lot less, but it does, right? So, I mean, that's the way that energy works. So heat given to surroundings. Final enthalpy is the products. Final enthalpy value of the products is less than for exothermic reactions. Then starting value of delta H is, then starting value of delta H is for the reactants. Well, I'm sorry, maybe then starting value of delta H is, or negative. I think that's what it's trying to say. Negative. But the products have less energy than the reactants do. Endothermic reaction, heat is absorbed from the surroundings. The enthalpy of the products is less than, more than, I'm messing up today, more than the starting value. So the products have more energy because they gained or absorbed heat from the surroundings. The starting value there is positive. So if we take a look, is this an endothermic or exothermic reaction? The delta H, or the enthalpy, which is just the heat change, is negative 65.2 kilojoules. So it is exothermic. For every mole of calcium oxide that you put in water to make calcium hydroxide, it releases 65.2 kilojoules. So this is kilojoules per mole. That means if I have 2 moles of this, it would be 130.4 kilojoules, right? So for every mole of this heat is released. Thermochemical equation, we could then write plus heat here because it's making this and giving off heat. So this person has chosen to write the amount there, and that is fine. Heat is written as a product in an exothermic reaction, and heat is written as a reactant in an endothermic reaction. So if we take a look here, this is positive. So that means that heat is a reactant because heat is being brought into it. Note, we would never put a minus in the equation. Heat is just either shown as something coming in or something going out. Reactant, product. So if we take a look here, energy in water is less than energy in hydrogen and oxygen. The quantity applies to basically the breaking and reforming of bonds. The breaking and reforming of bonds. How do they talk about energy for life cycle sciences? You guys know? What is the chemical, the all magical chemical from biology last year? ATP. So they probably told you that ATP, when ATP forms, it gives off energy. In reality, it's when ATP goes to ADP. When the bonds in ATP break, there's this energy there. When they reform to make the ADP, Some of that energy is in those bonds. The rest of that energy is what is released. That's the actual energy they're talking about. The energy is all there, and then when it's reformed, if that requires less energy, then that energy is given off, right? Just like it says here, hydrogen and oxygen have more energy than H2O. Well, a lot of energy is stored in this O2 bond because that's a double bond. That breaking of that double bond and the reforming of the two single bonds here, that's less energy. This is less energy. So where does the rest of the energy go? We know it can't be created or destroyed, so it's given off in this exothermic reaction. It's released. Oh no. 1 second. Technical difficulties. There we go. Is this bright enough? That's so good for you guys. Give it a second. Ah, the world is good. The world is good. It's a little blurry. Gonna fix it. There we go. All right. So the amount of heat released or absorbed during a reaction depends on the bond energies. We're going to talk about bond energies next Wednesday. That's next Wednesday. That's when we get into what's called the heat of formation and stuff like that. So keep that in mind. Give me 1 second. I'm trying to. This camera, my visualizer's messing up. Give it to me, come on. No? I'm gonna shut down this visualizer and reopen it real quick. It's not reading my camera for some reason. It's not happy unless it's looking crazy. Try that again. What do you mean? Yeah. There's not 14 of them. Yeah, there's some virtuals. Yep. But for some reason, I can't get this to share the screen anymore. I'm gonna need 1 second. I've got to switch out a component. I don't know if I can do that, because then you guys won't be able to see it. All right, let's see here. Power down completely. Repower. Mm-hmm. Yep, it just goes out the same number of decimals. It is not reading this camera right here at all. The only way I'm going to be able to do it is to take this. I'm just going to take it away from you guys, but I can go through it with you guys later. That didn't even work. I've not had this many difficulty before. Let me pause this recording and let me try to see if I can think. The recording. All right. So maybe a little smaller than normal, but I think we'll be able to get through what we need. So if we take a look, we are down here. So we just talked about how breaking and reforming of the bonds actually is what gives us that energy. That might be better than normal, huh? So if we take a look, if we have, instead of, we have 2 moles of H2 plus 1 mole of oxygen yields 2 moles of H2O, we get 483.64 kilojoules released. That negative just means, it tells me it's released. Energy is energy. 483.64 kilojoules is 483.64 kilojoules. For this particular thing, it is just released. So if we double the amount of hydrogen we have, and who was it that blew up the balloon in here? Yeah, Sydney blew up the balloon in here, right? And so she had a balloon that had maybe, 3 moles or 4 moles or something like that. The more moles you have, the more energy that's going to release. Also, the more products you're going to make. So if I double the amount of moles in all of this, I double the energy. 483.64 times 2. 483.64 times 2.
It's 967.28.
So 967.28. Should it still be negative? Yes. Yes was said, and that's exactly true. It's just more heat that's being released, right? So the sign should say the same. We can also flip-flop this. She ignited oxygen and hydrogen that were in the presence of each other with flame. That forwarded the reaction to water. But if I had water and I added some electricity to it, if I turn this into an endothermic process, if I flipped it, I add electricity to water, I can actually then make hydrogen and oxygen. Well, how much energy would I have to put into this in order to make it? Well, it's the same energy. It's the positive because I'm putting it into it, but it is the same energy. And that's kind of the cool thing. If this is happening, this much energy is going out. If I want the opposite to occur, then I've got to put that energy back in. So the easiest way to do problems like this, it says calculate the amount of heat absorbed when 5.66 grams of carbon disulfide is formed. Right? Well, it says that 89.3 kilojoules are absorbed every time 1 mole of carbon disulfide is formed. So what do I have to do to this in order to use this? Turn it into moles, right? So all of that math that I've taught you in the past is what you need. We take a look, 12.01 plus 32.06 times 2.
It's 76.13.
76.13 grams from the periodic table of elements is 1 mole. And every 1 mole formed requires 89.3 kilojoules of energy. As I said, this type of math is about 60 to 80% of all chemistry. If you can do this, you can do almost any of it. 5.66 divided by 76.13 times 89.3.
It's about 6.6391.
That's about 6.64 kilojoules of energy. That makes sense because we'd have nowhere near a mole. We have nowhere near a mole of this stuff. So it's going to take a fraction of it. It's funny, now it works perfect. Right? It's enough to waste 5 minutes, probably. All right, so let's try one more. What if they gave me the amount of energy that they had? For example, let's say that I have 5,000 kilojoules of energy. kilojoules of energy. And I want to find out how many, let's just do liters of water at STP, liters of oxygen at STP, right? So I have 5,000 kilojoules. It takes 483.64 kilojoules to make 1 mole of oxygen. Every 1 mole of oxygen at STP takes up how many liters? Every 1 mole of oxygen at STP takes up 22.4 liters of space. 5,000 divided by 483.64 times 22.4.
That would be about 231.5772.
231.6 liters of O2 I could make at STP with 5,000 kilojoules. If you wanted the grams instead, 5,000 divided by 483.64 times 18.02.
It's about 186.2955.
That'd be 186.3 grams of oxygen. So you can see that knowing this equation, knowing this energy, you can figure out the energy requirements of everything.
What did you do to get the grams again?
Just the molar mass of oxygen instead of the molar volume.
Oh, okay.
18.02, right? 16 plus 2.02. Now this is the cool thing. My red guys, this is what you want to read. This is on page 23. So basically what you're going to do is you're going to take solid magnesium and you're going to mix it with hydrochloric acid. We're going to use enough hydrochloric acid that it is in excess. But when magnesium reacts with hydrochloric acid, it produces magnesium chloride, hydrogen gas, and energy. But this is the accepted value. If you know hydrochloric acid is aqueous, so we will have the temperature of the HCl. We're going to see if that temperature goes up. And if that temperature goes up, we can calculate by knowing the change in temperature and knowing the mass of the HCl and using the specific heat capacity 4.184 because it's aqueous, we can calculate the amount of heat that was given off by that reaction. We will also have the mass of the magnesium, which we can then change to moles. So if we find the amount of heat, we can divide that by amount of heat by the amount of moles that we have, and that should give us a number that's close to this. So that's experimentally what we're doing. This time, because we don't want the acid to react with HCl, the acid to react with the aluminum calorimeter, we are going to use 2 styrofoam cups. Basically, you'll want to be very familiar with this procedure for when you come in so that it's a very easy transition so that you can get the mass of the empty calorimeter, the mass of the magnesium, the initial temperature of the HCl, the final temperature of the HCl, and then the mass of everything involved. Questions on that? No? All right, that's what I've got for today. Let me do this screen share. Oh, I'm upside down, aren't I? On my camera, I'm right side up. So screen share. So this is what I've got for you today, obviously. You can work ahead on any parts of these. Just by next Monday, you should be Up to page 26. Up to page 26. And then Wednesday, we'll be doing heat of formation. If you have a makeup test, you need to tell me before I leave here today, so I can put you on for over the weekend. Basically, I'm not going to be available over the weekend. This is, we're after Halloween. So my friends and I, my buddy Cody, he buys all the pumpkins real cheap off the farmers, the ones that didn't get sold. And then we fill them with explosives and we roll them down the hill at us. And then we shoot at them with assault rifles. So I will be gone all weekend doing crazy, stupid stuff, probably. So please make sure you won't be able to contact me. I won't get your message until Sunday night, probably, or Monday morning. So that's what I got for you for today. Have a great weekend. And do work, son. No, I don't know if you guys know that guy. Do you know the guy from, what is it, DC? You guys probably never seen it. Get work done. If you have any questions, by all means, I'm going to stay on here for the Zoom. I will have to end this, though, so I can post that, what we did today in the chat, in the channel, the calendar thing. Other than that, I'm out. Have a great weekend.
Mr. Jackson, can you